There we go. Recording is in progress, and we'll go ahead and we will post that on the website, the Canvas site, either later today or early tomorrow. Sometimes it takes a little bit of time for their end, the Zoom end, to handle things. All right, so as I say, I'm going to be working in chapter 5. Oh dear, come back here. All right, so chapter 5, 5.3. The binomial distribution. And before I even begin, one of the things that's going to be a challenge today, I have a wonderful calculator available, and you'll all be able to see what it is I am doing, but I won't really be able to see you and your calculator unless you turn your camera on and literally hold the thing up to the camera or something like that. So if there are issues, remember there are a lot of videos on all these keystrokes in Canvas, and I guess you'll also have more from the recording today. All right, so the binomial distribution. So a couple of things to get going. I'm going to give you a very basic definition. A binomial distribution has 4 main requirements. But before I do that, I want you to think, flip a coin. How many outcomes are there? 2. So anything that has 2 outcomes is an example of something that might fall into the binomial distribution realm. There's a couple of other requirements, but basically anything that has 2 outcomes have the potential to be a binomial distribution. And usually when there are 2 outcomes, we like to think of them in the following fashion. For simplicity's sake, we call them success and failure. Now, only because there are 2 outcomes, one of which will be the one we are looking for and counting, and the other one will be, well, the other outcome. Success and failure are honestly relative terms here. All right, so your binomial distribution has 2 outcomes. We're going to call them success and failure. Now, there are a couple of requirements for a binomial distribution, and they are a little bit difficult for students to check, at least some of them are. First off, we need a fixed number of trials. How many times are we going to flip our coin or whatever it is we're going to do? We've got to determine that up front. Each time we do a trial, there should be only 2 outcomes. The trials should be independent in the sense of chapter 4, in the sense that one outcome does not affect subsequent trials, and probabilities remain constant. So those are 4 requirements that we need for a binomial distribution. If any one of those requirements is not met, you do not have a binomial distribution. By the way, that doesn't mean there are no tools or whatever the case might be, but for an elementary stat class, we start with the binomial distribution, and it needs to have a fixed number of trials, 2 outcomes, independent trials, and probabilities need to remain constant. Out of these, students are very good at picking up on the first two, determining independence and determining if probabilities remain constant is still a little dicey at this stage of the game. So let me give you a couple of examples of things like a binomial that meet this requirement, and then one or two that don't, so we have something to compare them with. So we are going to flip a fair coin 50 times. We're going to determine a success, in this case, when the coin comes up heads. Failure when it comes up tails. So this is an example of a binomial distribution. You have a fixed number of trials. You have clearly defined two outcomes. Coins do not change their probabilities as they get tossed, and they don't affect subsequent tosses. So this is a nice example of a binomial distribution. Roll a die, and we're going to let success, I'm going to use the letter S now, equaling that the die comes up with a 5. F, not a 5. And we're going to roll this, and I'll use n equals 100 times. Is this an example of a binomial distribution? Do we have it set for a fixed number of rolls? Yes, we do. Now, you might think that this is not a binomial distribution because dice have 6 sides, and any one of those 6 sides could come up. But we're defining our success as coming up a 5 and coming up not a 5. So there are still only 2 outcomes, a success and a failure. So 5 or not a 5, yes, this is definitely definitely a binomial distribution. Roll a die again. S. Same thing. F. Not a 5. So we're going to roll this die until we get 3 5s. So I have the same 2 outcomes, 5 and not 5, but the difference here is that we're going to roll this until we get 3 5. The problem here is there is no fixed number of trials n. So no fixed n means that this is not a binomial distribution. But the other 2 are 2 outcomes and a fixed number of trials. And by the way, we will not set you up for failure and give you like really weird situations that somehow, I don't know, just barely fall through the cracks. That's not what we're about. we want to make sure you can go ahead and actually deal with these problems. So that's the definition and examples of a binomial distribution. Now, I am going to give you some notation. N, that is our number of trials. The variable X is the number of successes S in N trials. P with the big X, P with X is the probability of exactly X successes in those N trials. And by the way, I know I'm probably going a little bit faster than I go in class. That's because you're not all in front of me, like, and I can't see you scribbling frantically. So I'll apologize about that straight up. And I will note, that I am recording this. So don't get all stressed about that. Some of you have already found your way to the chat. And if you have questions, you can definitely put them into the chat. If you have comments, please place them there also. Or you just unmute and shout it out. That's just, and I think there's some crazy way to like raise your hand. And hopefully I can keep track of that.
There is a way. You just go. So for everyone, sorry to interrupt. There is a way to you just have to go to reactions, and in the reactions you can send an open mouth, flat joy, thumbs up, no, yes. And you can also, and at the bottom there is a hand and it says raise hand, and if you can see my hand, that's what it is. And then Professor Moss,
Thank you.
You can just lower your hand.
There you go. We actually, some of our councils, this is the way we do our voting. So notation, the probability of exactly X successes in N trials. And again, S is the definition of success. F is the definition of failure. All right, so now we do, and I'm going to try this in the way opposite of what I usually do. And we're going to see how it goes down. Now, we work two kinds of problems with this. And let me give you an example. We are going to flip a coin. Well, actually, no, hold on. Let me do one other thing. Let me come back here and put a couple of other things into the notation I'm going to need. So the letter P, little p, that's the probability of success in any one trial. We have Q, and that's the probability of a failure in any one trial. And we need to note that Q is equal to 1 minus P. So whatever Q is, excuse me, whatever P is, we know what Q is. All right, so now that I've got that out of the way, let me come back here to my example that I was going to discuss. And as I say, I'm going to start with a very simple, basic example. We're going to take a look at what our calculator does for us and how it does it. And then we're going to take a look at what the formula actually says and how it does its thing and what the connection is. So hopefully that goes down okay. So as I say, we will flip a coin. We're going to flip it n equals, let's make it n equals 20 times. We're going to let our success equal heads. So when my coin comes up heads, that's my success. X is going to be the number of heads I see in those 20 flips. So first I'll talk about P. That's the probability of a head in any one flip, right? A probability of a head in any one flip. Now you should remember that from chapter 4. If my coin is fair, it's 1 out of 2. The probability of a failure or a tail is also 1 out of 2 if my coin is fair. So I know P is equal to 1/2 and Q is also equal to 1/2. And I'll use some of this a little bit later, and then I'll use most of it eventually. So if the number of if X is the number of heads and success is the number of heads in the 20 flips, the possibilities for X are 0, 1, 2, all the way up to 20. It'd be very unlikely to get 20 heads in the 20 flips. It'd be pretty much equally unlikely to get 0 heads in 20 flips. So that's the possibility for X. And we have two basic kinds of questions. We have the single P of X question, and then we have the sum of many P of X's, that question. And we have two tools that, work with this, and they work with this very, very well. The single P of X uses something called binomial PDF, short for probability distribution function, or binomial probability distribution function. So that is the probability tool I use for the single P of X. And for the sum of many, I use the binomial or the binomial CDF for cumulative distribution function. So these are the tools I use for my binomial distribution probability questions. It does a very, very, very good job. So let me go ahead and run through a question or two of these, and then we'll take a look at the formula. And then we'll take a look at some of the subtleties of these style of questions. And then I also want to look at one or two of your homework questions. All right, so we're still in the land of the coin toss. Like you're down at the boardwalk or something. What did I say? N was equal to 20. S is equal to heads. P is equal to 1/2. And by the way, yes, that's a 0.5, but I also like the 1/2 notation. It works very, very well with my calculator. And it really is helpful on some other types of problems, as you'll see. So coin toss. S is heads. We want to find the probability of and we're going to start with exactly 10 heads. So what we're looking for is the probability of 10 heads. So that's what we're looking for. So I'm going to go ahead now and go over to my calculator. I've got a built-in calculator, and I'm going to share that screen. And this actually makes my job really nice. It was a real pain before trying to do the calculator with the camera. All right, so you should still see me up in the corner if you desire, or you can turn that off. Anyway, there's my TI-84. Now, actually, let me do one thing before I do this. Let me unshare. I know that seems rude. So this is a single P of X. And anytime I see that word exactly, that is a single P of X. And I know I'm going to use my binomial PDF tool. A very common mistake to make in this chapter is to pick up the wrong tool. So the binomial PDF tool. All right, so let me go back now and try that share thing again. There we go. There's my calculator. Now, we've, and I believe I mentioned this in class on, I guess it was last week now, your distribution key right here in blue, right up above the vars key. Oh, no, I know where I did that. I did that in my other lab, not your lab, the other lab. So you see where it's there in blue? So second distributions. We do a lot of work through this screen, a lot of work. And if I scroll down, I've got to scroll down quite a bit. And there are different numbers on different versions of the TI-84. But there is my binomial PDF function and my binomial CDF function. Now, let me select the PDF function. And before I type in anything else, I want to point something out. I have a place for trials, P, and an X value. Now, don't worry about the paste. And before I go ahead and start punching buttons like crazy, I want to point something out. Let me go back to the distributions and scroll down here to the CDF tool. The things I input are exactly the same as the PDF tool. They do different things though. So you've got to be very aware that you are in the correct tool. A single probability. The exactly word means I need PDF, and that's not where I am. So, binomial PDF. I can enter in my trials, 20. I enter in P, 1 divided by 2. We are interested in the probability of exactly 10 heads if we flip our coin 20 times. We'll paste that in, and there we go. And once it's in there, I'll hit enter, and I'll get a 0.1761 or a 0.176. I'm going to note that 0.176. The 3 significant digits.
The X value is 20, right?
Pardon me?
The X value is 20, right?
The X value is 10. I'm going to go over the keystrokes again. Second distribution. PDF. The N is the 20, and we are interested in exactly 10 heads.
Okay, thank you.
In the 20 flips.
Thank you.
You're welcome. Now, let me talk a little bit about where this number comes from. Before I do that, though, let me ask, those of you that are trying these keystrokes, I'll remind you, we do have video of them already up in Canvas. And I'll ask, did that work for people? If it didn't work, unmute. I see Acela, you have a question there? You can unmute, perhaps. Or you can put your question, is it, oh, there is a question in the chat. It's 1 minus P. Q is equal to 1 minus P. So let me explain a little bit about where this comes from. All right, this is going to get really, really, really mathy. I'm going to give you a very ugly formula. Well, it's a formula that I like a lot. A very ugly formula. And then we're going to go ahead and show you how this actually works. All right, so we have a formula for P of X. And I do believe you can actually find it somewhere in that chapter 5. It's in a ridiculous, ridiculous place, but there is a formula in there. And this is equal to n choose X times P raised to the X times Q raised to the n minus X. And that, if you don't remember, is n factorial over n minus x factorial times x factorial, P to the X times Q to the n minus X. And OMG. Now, I am not suggesting that we actually use this formula to do our problems. But I'm going to do it once for us on the calculator just to verify our results. You follow me? I'm not going to actually require you to use this formula. I can't say that enough. So let me share my calculator screen. And we'll start with let's see, we have 20 trials. We are interested in 10 successes. We're going to multiply those number of choices by the 0.5, and I use my decimal now, and we'll raise that to the 10th power. We're going to multiply that by the Q value, which is also a 0.5. We're going to raise that to the 20 minus 10 power, and that should give me pretty much exactly the same thing, and sure it does. But we're not going to use that formula. We're going to use the binomial PDF formula. So if people want, you can go ahead and try that out. But if it doesn't work for you, don't stress. Realize that your calculator does a great job for you as it is. About the only thing else I will say is some of you have the older version of the TI, which doesn't have the fancy stat wizards. So when you type in and select your binomial distribution PDF, that's all you see. You don't see the trials and all that good stuff. You'll have to type that in directly, 20, and then you'll have a comma key. We've talked about this before. A comma key, 1 divided by 2, a comma key, and a 10, and then you close up the parentheses, and you'll be good to go. But that's if you don't have your stat wizard. If you do have a stat wizard, make sure that stat wizard is turned on, and you'll get all the help that you that you probably want. So binomial PDF is how we handle this problem. We don't use the formula. As pretty as it is, we just don't use it. So excuse me, pardon me, let me clear my throat. In fact, I'm going to have you hold on for 1 minute. I'm going to stop my sharing, and I'm going to mute, and I'm going to go grab a soda. Hold on. See, just like class. Same flavor, everything. All right. So now we're still flipping coins. S is equal to heads. All right, so now I want to talk about the sum of many. And in that notion here of the 20 coin flips, we want to find the probability of at most 8 heads. Probability of at most 8 heads. All right, so at most 8 means X must be less than or equal to 8. The number of heads less than or equal to 8. So we're looking for the probability of maybe 0 heads, maybe 1, maybe 2, maybe all the way up to 8. Now, these outcomes are mutually exclusive. You will either have 0 or 1 or 2 or all the way up to 8. So I can add those probabilities together. This is really like a crazy addition rule from who knows where. So this is a sum of many. And again, I would say that most of the issue people will face is kind of with the language once you figure out how the tool works. So we're going to calculate this with the binomial CDF tool. And this binomial CDF tool, excuse me, let me go ahead and share my calculator screen, and we'll see how this works. Let me get rid of you. Okay. So second distribution. Oh, I'm sorry, I went right by it. There's a lot of good stuff in here. Really fun stuff. You'll notice that it has essentially the same screen. Now, before I go and fill that screen in, let me stop my share and come back to the notes for a moment. This CDF tool always works in the same way. It always starts at 0, and you tell it where to stop. That is the X that you see in the CDF tool. That is the X value that we need to place in. It will start at 0, and it will go until we tell it to stop. And we're going to tell it to stop at X equals 8 heads. So it's a subtlety, but it's important. So 20 trials. I said 20 trials. 1 out of 2 for X. Excuse me, for P. For X, we have 8 heads. We're going to go ahead and paste that in. And we get 0.2517, so 0.252. So you see how that works? If you're trying those keystrokes, let me go through them again. CDF, 20 trials, 1 out of 2 chances. The outcome is ahead. X is at most 8 heads. We'll paste that little puppy in, and there we go.
Can you please go back to the notes?
Yes.
Thank you.
Mm-hmm. I'm going to do one more. This time, it'll be less than 12 heads. Less than 12. That means we are not going to include the 12 when we have the probability 0 less than or equal to X up to and including 11, but not 12. So you'll go back to the CDF. I'll wait, I'll let you guys try that on your own. I'll be quiet for a moment or two here. Let's try that on your own. In fact, I'm going to run an errand while you guys do that. I'll be right back.
How many trials are we doing?
The one you see right there, 0 up to and including 11. Try that. I'm back. All right. And again, this is being recorded, and we will publish that as soon as it becomes available. So, sum of many, binomial CDF, probability of less than 12 heads means somewhere between 0 and 11 heads would be what I see. Let me come back to my calculator and pick it up. CDF, 20 trials, 1 out of 2. This time the value is 11. So it's going to add the probability of 0 heads and 1 head and 2 all the way up to 11. Blow on it once for luck. There we go. 0.7482, so 0.748. If you're punching the buttons, are you guys seeing that? I hope you are. There's a good crowd of you here today. I'm glad you're able to make it, and I really do hope people are surviving okay, and no one is too severely impacted. I just basically can't get to Salinas. Highway 1 is all jacked up. So, yes.
Oh, I was gonna I know this is off topic, but I was just wanted to say, like, where I live, the bridge I have a bridge connecting, there's a bridge on, I think it's Highway 68, or I don't know. But the water is so close to the bridge near Reservation Road.
Yes. Yeah, it's just it's crazy.
And I'm like, oh, I don't want it to, like,
I understand.
I'm like, I don't want it to flood it. It's just scary.
So now there is some subtlety to this sum of many issue. And let me show you. Let's consider the same thing. We're still working with our coins. N is still 20. P is still 1/2. S is still heads. And let's look at the probability of at least 10 heads. All right. So this time, at least 10. So the probability that we have for X is maybe 10, maybe 11, maybe 12, all the way up to maybe 20 heads. And in terms of an inequality, a symbolic inequality, we have the probability of 10 less than or equal to X less than or equal to 20. Now, here is the issue with this problem. Let me bring back the previous page. I'm going to take this away. I'll be bringing it right back in just a moment. That binomial CDF always starts its counting at 0, and it always ends where we tell it to. It must start at 0 and end at a value we give it. So, when it comes to this particular statement, starting at 10 and going to 20, that's an issue. The binomial CDF zero to whatever value of X we give it. That's the way that works. Now, how are we going to work around that problem? And This is the way we do it. And it's not overly difficult. You just have to see it a couple of times. You'll get an idea. So let's think about what X must be in terms of this whole thing. It could be 0 heads or 1, maybe 9 heads, maybe 10 heads, maybe 11 heads, maybe all the way up to 20 heads. Now, the 10 to 20 heads, these guys here, these are the outcomes I am interested in. This is my, I'm going to call it A for now. The rest of the outcomes, everything but A, that set of outcomes is the complementary event. And what I need to use to find what I need over here, the probability of A is equal to 1 minus the probability of the complement of A, that A bar. We introduced this in chapter 4 because we need it here. So the probability of getting 10 or more heads out of the 20 flips is 1 minus the probability of getting somewhere between 0 and 9 heads. That is what we want to do. You'll notice that this is the complement of that event A. So this has to be set up in terms of the complement. Now, the nice thing is my calculator works with this just fine. So follow me over to my calculator in the best digital sense. There's my calculator. And I'll just go 1 minus. I'll literally go 1 minus, and then I'll run and pick up my binomial PDF or CDF function, I should say, with the 20, the 1/2, and this time the value is 9. I'll paste that in there, and there we go. So once that gets in there, I can say enter, and I get a 0.588. Let me do that again. 1 minus 20, 1 out of 2, 9, and then paste him in. And there we go. So that is really the tricky part, if you will, of this presentation. So let me stop my sharing. It is 1:23 right now. I would like to take a break. I'd like for us to take a break, just like a regular class. I'm going to go ahead and mute my video and mute my mic. Goodbye, video. I will be back in 10 minutes. So at 1:33 or maybe 1:34. Anyway, take a break, consider what we had. And remember, we're recording this, even our break. This will be fun. Bye-bye. All right, I'm back. Turn that on again. So there we go. All right, so we have a couple of issues with this. I'll remind people that the binomial CDF tool is strictly a count up tool. It always starts at 0 and it goes as far as you want it to go. And that's the way that works. So any probability you're interested in that is a sum of many that begins with something other than 0, it means you're going to be in this particular realm. Let me give you another example here. Still working with the coins. All right, so the probability the probability of at least one head. Now, this is a very common setup. Very often, we want to know the probability of at least one of something occurring, especially if it's like a bad thing. We want to prevent that from happening. So we like the probability of at least one as a very common question. Now, x could equal either a 0, a 1, a 2, a 3, all the way out to 20. So the set we are interested in is this thing here. This is my set A. It does not begin at 0. So I've got to set this up in terms of the complement. The complement in this case contains just a single outcome. The outcome of no heads at all in those 20 flips. So this is an example of what we call the probability of at least 1 is equal to 1 minus the probability of none. So in our case, we're looking at the probability of 1 less than x all the way up to 20. That's 1 minus the probability of exactly 0 heads. And what's important to remember or note about this that's a single P of x. So that's the binomial PDF pool, not the CDF in this particular instance. So this number will be very, very close to 1 because it's highly unlikely to get zero out of those 20 flips, 0 heads. So that's unlikely. So let me go ahead, share my calculator screen. And we'll have 1 minus, and this time we'll make sure we pick up the PDF tool. And it does say PDF, so read things carefully. Oh, look at that, 0.999999993. Oh, let's see. I want to get all those 9s in there. 1, 2, 3, 4. Is there 5 or 6 in there?
Can I ask a question?
Yes.
What is the difference between the binomial PDF and the binomial CDF? What's the difference?
The PDF only works with a single value, while the the binomial CDF, and I'm going back to a previous screen here, CDF gives you a sum. A sum, and that's the big difference.
Okay, thank you.
And you've got to read the question carefully to determine whether you have the PDF or the CDF. I'm going to go ahead and do one more example, but I'm going to do it from your homework. So I'm going to pick one from your homework. Some of you have already talked to me about some of these problems. And let me go ahead and get this up and running. All right. I'm sorry, give me a moment here. Oh, there we go. Good Lord, that was a pain in the butt. Sorry, scrolling through everything. Let's see. All right, let's take a look at, I'm going to take a look at number 21 in your problem set. Let me share my screen just so you know what I'm looking at. And this is out of your text. It's one of the assigned homework problems. It's number 21 right here. Approximately 8% of all people have blue eyes. Out of a random sample of 20 people, find the following. And I'm not going to do all of them, but I want to take a look at a couple of these. So this is a nice example of the kind of problem that you will see on quizzes and on exams. So I note that everything I need will be given to me in this particular instance. I'll note that if I read the introduction to the problem here, there are 20 people. So I know that my sample size is 20. So n is equal to 20. I know since 8% of all people, 8% of all people have blue eyes, and we're talking about blue-eyed people, P is equal to 8%, or better yet, 0.08, which is what I need, not the 8%. And finally, we're looking for people who have blue eyes. So success, blue eyes. All right, so let me stop my sharing here and come back over here. And there's my data that I've been given. So let me go ahead and answer a couple of the questions. What is the probability that 2 have blue eyes? 2 have blue eyes. So this is the probability of exactly 2. This is the binomial PDF. And I get that from the way the question is worded. 2, no more, no less. PDF 2.
So is all the problems going to be based on the binomial PDF?
No, we got to read the question before we determine if it's PDF or CDF.
Okay.
The first one, the probability that 2 of them have blue eyes is a PDF question. It's a single outcome, exactly 2. So on my calculator, I'll pick up the binomial PDF tool. We have 20 trials again. P is 0.08. The X value in question is 2. I'll paste that in. There's no 1 minus this time. And I get a 0.271. I think the book asks for 4 decimal places, in which case it'd be 2711, but I'll still round to 3 because that's what we do. So that was what? That was A. Now, I'm going to jump down to C. Less than 2 have blue eyes. So it's the less than 2 that tells me that this time I have the binomial PDF. So less than 2, that means X is equal to either 0 or 1. So we're looking for the probability that 0 less than or equal to X, less than or equal to 1. So this time it's the binomial CDF tool.
We have to use the 1 minus?
Not this time because we're counting up from 0.
Okay.
And I get a 0.517. And that's because the way this is worded, we're starting our counting at 0 and we're ending it at a value we choose, which in this case is 1. And then I think D at least 2 of them have the blue eyes. So in this case, X is equal to 2, 3, all the way out to all the way, maybe 20. So at least 2. And I'll note that in this case, because it's at least 2, we're not counting, starting our counting at 0 like we did up here. We're starting it at 2 and we're taking it up to 20. This is where I need the 1 minus. So the probability that X is somewhere between 2 and 20 inclusive is 1 minus the probability X is between 0 and 1. And you'll notice that with the complement, we've got to stop that 1 before the x's begin. So this time we need the 1 minus. And there we go. When it goes in, 0.08, from 0 up to 1 inclusive. Plug that in, and 0.483. So those are the subtleties that that we see. Hold on, I'm messing with things. No, I should not have messed with things. Hold on, I'm still playing. All right, okay. Still playing, sorry. All right, so there we go. So as I say, those are the very basic sorts of questions that we ask when it comes to binomial distributions. There is one other topic that I'll need to address, and then I want to look at one specific problem from your homework. These are the binomial parameters. So anytime I have a binomial distribution, I have the parameters. I have a mean, I have a standard deviation, and I have a variance. The mean, mu, is equal to n times p. The standard deviation, sigma, is equal to the square root of n times p times q. Q is 1 minus p. And the variance, sigma squared, is n times p times q. And we actually need these formulas. They're not built into our calculator. So for the blue eyes problem, n was equal to 20, p was 0.08. That means q is 1 minus 0.08, or a 0.92. And if I select 20 individuals at random, and I'm looking for blue eyes, the mean number I can expect is mu is equal to 20 minus 0.08. My calculator finds that quite easily. I don't even feel the need to demonstrate that. Oh, there we go. I don't feel the need to demonstrate. Hold on, I'm missing something. There we go. Good Lord, I lost track of some stuff. It's strange. So we got the 20 times 0.08. That gets me to 1.6 people. My standard deviation is the square root of 20 times a 0.08 times a 0.92. Or sigma equals And again, your calculator finds this without issue. And I get a 1.2 and change. So we get 1.2 people. If I want to find the variance, that's sigma squared. That's 0.08 times a 0.92. And I get a 1.5 when I round to one decimal place. People squared. So anytime I I'm sorry, I'm still messing with stuff. I haven't played around with this in a little while. There we go. There we go. Okay. Are there any questions about the binomial parameters? They're very basic. They're very easy to use. However, you've got to remember you need the formulas. Oh, and I guess you need this little guy too. Don't forget him. Now, let me look at a very specific problem from your homework assignment. And then I'll want to talk about chapter 6 for just a little bit. But before I get into your chapter 6, I want to take a look at this really weird problem that you encounter somewhere in chapter 5. Yes, let's talk about problem number 31. And by the way, this is how this kind of statistics is used in the real world. If you've ever flown on an airplane and gone to the airport, maybe you've realized that sometimes airplanes or airline carriers sell more tickets than they have seats for. Yes, plane only has X number of seats and they sell more than that. They do that because they know not everyone will show up. For whatever reason, there's always issues somewhere with someone. Believe me, as someone who teaches a class and I see who shows up, I know that's true. So let's take a look at number 31. A small regional carrier accepts 20 reservations for a particular flight with 17 seats. There are 15 reservations went to regular customers who they know will arrive for the flight. So 15 out of those 17 seats on the plane are already spoken for. Each of the remaining passengers will arrive at the flight with a 60% chance independently of each other. So there's two questions. The first question, find the probability that overbooking occurs. That's the first one. In other words, more people show up than there are seats for. Then we want to find the probability that the plane actually has empty seats when it takes off. All right. By the way, the handout I had for class, planned for class, incorporated this problem. That's what we were going to do on Tuesday, or an example of this. So let me go ahead and stop my sharing and summarize what it is we're looking at. So 20 seats, 15 accounted for. there's a 60% chance the remaining people show up. So we've got to come up with a way of setting this problem up and determining what we're actually working with. Because I guarantee you it's not the 20 and it's not the 15, although the 60% is the P we use. So 0, 1, 2, 3, 15, 16, 17, 19, and 20. All right, so here's the way we want to look at it. We know that 15 seats on the plane are going to go to the people that have shown up. Our plane only has 17 seats. So really what we're looking at in terms of interest is this right here. We have the number of tickets sold and the number of seats available. So you can see we have 2 seats available, yet we sold 16, 17, 18, 19, 20. We've sold 5 tickets more than we have seats available. All right. Now, so our problem is really not this guy up here at all. It's really this one here. N is equal to 5. P is equal to 60% or 0.60.
Where'd you get the 5? Sorry.
Right up here, from right here. I'm in trouble if everyone shows up. There's 5 people that might show up, and I only have 2 seats available. That's the problem. 20 people are coming maybe all together, 15 for sure. That means 5 we don't know about, and that's the group we care about. Now, this is a very advanced problem, okay? You'll never see a problem like this on a quiz or an exam. I promise you that. So N is equal to 5. We overbook. Let's see. We're in trouble if we get 3, 4, or 5 people show up. That's where I'm in trouble. If none of these 5 show up, I'm fine. If one of these 5 show up, they have a seat. If 2 of these 5 show up, both of those people have a seat. If 3 people show up, someone doesn't have a seat. Same problem with 4, same problem with 5. So I'm in trouble if we overbook. So the probability that X is somewhere between 3 and 5 is 1 minus the probability is X is somewhere between 0 and 2. So this is the probability that we overbook. So if I put that on my calculator, clear that out. So that's 1 minus CDF. I have 5 trials now. 0.60 is a probability someone doesn't show. Excuse me, someone shows. The X value in question is 2. We'll paste that in there. And we got a 0.683. So better than 1 in 2 chances that we have an overbooking. Now the
X value 2.
Pardon me?
Sorry, the X value is 2.
Yes. The X value is 2. It's got to be 1 less than what we're interested there, because this is
definitely the keystrokes and how we got 35, because I'm getting a different answer.
1 minus And you got to make sure you use the CDF tool, not the PDF. If you use the PDF, you'll get the wrong answer. That's a very common mistake to make. And one of the things I can't do right now is look at everyone's calculator. So CDF, 5 trials, 0.60. The value is 2. Paste that in. And you got to get the 1 minus in there also. So
I understand.
So there we go.
I put in 20 instead of 5.
Now the empty seat one's a little bit different. The empty seat one, that means none of these 5 show up. In other words, at least one of these seats has to be empty. There's an empty seat if x is equal to a 0 or a 1. If x is equal to 2, both those seats are occupied. If x is equal to 3, we're into the overbooking stage. So the empty seats is 0 and a 1. There's no 1 minus here. If we're starting at 0. But again, it is the binomial CDF function. So this time, still 5, still 0.60. This time we'll take it from 0 up to 1. And again, when you're trying this at home, make sure you're using the CDF tool. 0.07870. So there it is, to 3 significant decimal places. And there we go. So what I'd like to do now is just to do a little bit of summary here because we've talked about an awful lot. So we have our binomial distribution. We'll have n, p, q, and x as the variables in question. We have the single p of x. Usually you can find the word exactly instructors usually try to use the word exactly when they write these problems out, unless they're trying to be cute. That single p of x is the binomial PDF function. And then we have the sum of many. And they can be used with at least, more than, at most, and less than. There's a number of ways to speak of these. I'll put them in a group quote. The first 2, we need a 1 minus p of some sort. The second 2, we just need the p value. And this is the binomial CDF function. The binomial PDF and the binomial CDF function. And we have the parameters. The mean equals n minus p. Standard deviation, the square root of npq, with q equals 1 minus p, and our variance npq. And we need those formulas. We usually take those to 1 decimal place. Because x is usually a whole number, so we want 1 more. And there we have it. All right. Let me ask if people have pretty much any questions. I thought I would get started in chapter 6, but really we only have a handful of minutes. And we all just got done dealing with our first online lecture. Let's see. No, stop my sharing. Go away. There we go. Okay. Are there any questions? Give you a moment. Nothing, you can shout them out, or you can place it in the chat. All right. Well, I'm going to go ahead and say goodbye then. We're going to go ahead and try to do this for lab on Friday also. We'll have more examples here. Ideally, what I'll do is I'm going to push out that material to you guys first. So you'll have that when the lab starts, and we'll see how it goes. And then we'll take next week as it comes. There's a chance I might still be up here next week also. Anyway, I thank you very, very much for joining, and I will go ahead and I'll end the meeting. Thank you, really, thank you. Yeah, thank you so much for everyone for coming. I really do appreciate it. Stay dry and stay safe.